Jungle. Audio Jungle.
Optical fiber digital line system. 3.2 Understand dense wavelength division multiplexing DWDM. 3.2.1 Explain dense wavelength division multiplexing DWDM. 3.2.2 Visualize the block diagram of DWDM. 3.2.3 Discuss the channel frequencies or wavelengths and channel spacing of DWDM system according to ITU standards. 3.2.4 Explain the main components of DWDM system. A. Transponder. B. Multiplexer and a multiplexer. 1. Fiber Bragg gratings FBG. 2. Multi-layer interference filters. C. Optical amplifier erbium doped fiber amplifier BDFA. D. Optical add-drop multiplexer ADM. Block diagram of DWDM. Dense wavelength division multiplexing DWDM is a technology that puts data from different sources together on an optical fiber, with each signal carried at the same time on its own separate light wavelength. Using DWDM, up to 80 and theoretically more separate wavelengths or channels of data can be multiplexed into a light stream transmitted on a single optical fiber. Dense wavelength division multiplexer WDM. Multiple channels of information carried over the same fiber, each using an individual wavelength. Unlike CWDM, channels are much closer together. Each wavelength behaves as if it has its own virtual fiber. For example, transmitter D1 communicates with receiver R1 as if connected by a dedicated fiber, as does T2 and R2, and so on. Optical amplifiers needed to overcome losses in mux/demur and long fiber spans. Block diagram of DWDM. 1. Transponder. 2. Multiplexer and a multiplexer. 3. Optical amplifier. 4. Optical add-drop multiplexer ADM. The channel frequencies or wavelengths and channel spacing of DWDM system according to ITU standards. Standard channel plan developed by the International Telecommunications Union ITU. 400, 200, 100, and now 50 GHz spacing between channels. Starting at 1530 nanometers and going through 1560 nanometers channels. Main component of DWDM system. Transponder. Transponders convert optical signals from one incoming wavelength to another outgoing wavelength suitable for DWDM applications. Transponders are optical OEO wavelength converters. A transponder performs an OEO operation to convert wavelengths of light. Within the DWDM system, a transponder converts the client optical signal back to an electrical signal OE, and then performs either 2R reamplify, reshape, or 3R reamplify, reshape, and retime functions. Main component of DWDM system. A transponder is located between a client device and a DWDM system. From left to right, their transponder receives an optical bit stream operating at one particular wavelength, 1310 nanometers. The transponder converts the operating wavelength of the incoming bit stream to an ITU-compliant wavelength. It transmits its output into a DWDM system. On the receive side, right to left, the process is reversed. The transponder receives an ITU-compliant bit stream and converts the signals back to the wavelength used by the client device. DWDM terminal multiplexer. multiple wavelengths are all within the 1550 nanometers band, created by multiple transmitters and operating on different fibers are combined onto one fiber by way of an optical filter, MUX filter. This device contains a one wavelength converting transponder for each wavelength carried. It receives an input optical signal, converts it to an electrical signal, and then retransmits it as an optical signal, a process abbreviated as OEO, using a 1550 nanometers laser beam. The MUX multiplexer takes a number of 1550 nanometers optical signals and places them on a single optical fiber. This terminal multiplexer may also contain an EDFA erbium-doped fiber amplifier to amplify the optical signal. DWDM terminal demultiplexer. At the receiving end, the DMUX demultiplexer separates all of the individual wavelengths of the composite signal out to individual fibers. The individual fibers pass the demultiplexed wavelengths to as many optical receivers. This device breaks the multi-wave signal back into individual signal. These may be sent to OEO output transponders before being relayed to their intended destinations, client layer systems. Fiber Bragg grating FBG. A fiber Bragg grating FBG is a type of distributed Bragg reflector constructed in a short segment of optical fiber that reflects particular wavelengths of light and transmits all others. This is achieved by creating a periodic variation in the refractive index of the fiber core, which generates a wavelength-specific dielectric mirror. A fiber Bragg grating can therefore be used as an inline optical filter to block certain wavelengths, or as a wavelength-specific reflector. When a Bragg grating exists in an optical fiber, it will reflect a specific wavelength dependent on the period of the Bragg grating and the index of refraction of the optical fiber. This calculator finds the period of Bragg grating needed for a predetermined wavelength and index of refraction. Multi-layer interference filters. Multiplexing 4 wavelengths using thin film filter. Filters labeled TFF2, TFF3 and TFF4 pass wavelengths lambda2, lambda3 and lambda4 respectively, and reflect all others. To separate DMUX the wavelengths, the directions of arrows are reversed. Since a light beam loses some its power at each TFF because the filters are not perfect, this technique works for only a limited number channels, usually specified as being 16 channels, 0 or less. For DWDM, 8 channels with 50 GHz and 100 GHz. Erbium-doped fiber amplifier. Erbium is a rare earth element that, when excited, emits light around 1.54 micrometers, the low-loss wavelength for optical fibers used in DWDM. A weak signal enters the erbium-doped fiber, into which light at 980 nanometers or 1480 nanometers is injected using a pump laser. This injected light stimulates the erbium atoms to release their stored energy as additional 1550 nanometer light. As this process continues down the fiber, the signal grows stronger. The spontaneous emissions in the EDFA also add noise to the signal. This determines the noise figure of an EDFA. Optical add-drop multiplexer (OADM). The optical add-drop multiplexer selectively removes drops a wavelength from the multiplex, then adds the same wavelength but with different data. This OADM is designed to only add or drop optical signals with a particular wavelength. From left to right, an incoming composite signal is broken into 2 components, drop and pass-through. An optical add-drop multiplexer allows access to individual DWDM signals without conversion back to an electronic domain. In the example below, visible colors are used to mimic DWDM wavelengths. Wavelengths 1, 3 and 4 enter the OADM. Wavelengths 1 and 4 pass through. Wavelength 3, blue, is dropped to a customer. Wavelengths 2, green, and a new signal on 3, blue, are added. Downstream signal has wavelengths 1, 2, 3 and 4. 3.3 Understand passive optical network. 3.3.1 Describe passive optical network (PON). 3.3.2 Describe the main components of PON. A. Optical line terminal volt. B. Optical network unit ONU. C. Optical network terminal ONT. D. Splitter. 3.3.3 Categories 5 Types of PON. A. Synchronous transfer mode (APON). B. Broadband PON (BPON). C. Gigabit PON (GPON). D. Ethernet PON (EPON). E. Gigabit Ethernet PON (GEPON). Understand passive optical network. Passive optical network (PON). Network in which fiber optic cabling instead of copper brings signals all or most of the way to the end user. It is described as passive because no active equipment, electrical power, is required between the central office or hub and the customer premises. Depending on where the PON terminates, the system can be described as an FTTX network, which typically allows a point-to-point or point-to-multipoint connection from the central office to the subscriber's premises. Types of PON are APON, BPON, GPON, BPON, GPON, WPON, CPON. Passive optical network (PON). A. Optical line terminal volt. B. Optical network unit ONU. C. Optical network terminal ONT. Optical line terminal volt. Optical line terminal is the network's control processor. This unit resides in the local CO central office, cross-connected to the video and data networks that will be delivered to your home. It consists of a special DFB distributed feedback calibrated laser that is always on. The old control card acts as a traffic signal to the remote ONTs for complete data, video throughput upstream and downstream. Optical network unit ONU. ONU converts optical signals transmitted via fiber to electrical signals. These electrical signals are then sent to individual subscribers. In general, there is a distance or other access network between ONU and end user's premises. Furthermore, ONU can send, aggregate and groom different types of data coming from customer and send it upstream to the old. ONU could be connected by various methods and cable types, like twisted pair copper wire, coaxial cable, optical fiber or Wi-Fi. Optical network terminal ONT. Actually, ONT is the same as ONU in essence. ONT is an ITUT term, whereas ONU is an IEEE term. They both refer to the user-side equipment in GPON system. But in practice, there is a little difference between ONT and ONU according to their location. ONT is generally on customer premises. ONT location is at the customer's premises. Its purpose is to use optical fiber for connecting to the PON on the one side, while interfacing with customers on the other side. Splitter. A PON splitter takes one input and splits it to broadcast to many users, cutting the cost of the links substantially. Furthermore, since PON splitters are bidirectional devices, signals can be sent downstream from the central office broadcast to all users, and signals from the users can also be sent upstream and combined into one fiber to communicate with the central office. The PON split can be one unit in a single location or several splitters cascaded. To reduce the amount of fiber in a network, cascaded splitters can be used by placing splitters nearer the user. This is usually done when houses being served are clustered in smaller groups. Optical splitter. A passive network device used to divide one incoming signal into multiple signals. This is accomplished by using waveguide technology to split the optical power among several output fibers. Two types of optical splitters used in PON system. 1. Fused biconical splitter FBT. Support only 3 wavelengths: 850 nanometers, 1310 nanometers and 1550 nanometers. Can split up to 132 at maximum split ratio. 2 planar lightwave splitter PLC. Support whole range of wavelengths: 1260 nanometers up to 1650 nanometers. Can split up to 1 to 64 at maximum split ratio. Understand passive optical network. Optical line terminal VOLT. The ELT is located at the service provider's central office. It provides the interface between PON and the backbone network. Optical network unit ONU. The ONU is located near end users. It provides the service interface to end users. Optical distribution network ODN. The ODN in PON connects the ELT at the central office and owners near user homes by using optical fibers and splitters. The ODN usually forms a tree structure with the ELT as the root of the tree and owners as leaves of the tree. 5 types of PON. Synchronous transfer mode (APON), broadband PON (BPON), gigabit PON (GPON), Ethernet PON (EPON), Gigabit Ethernet PON (GEPON). Types of PON. APON. Though it is rarely appear in our current fiber network project, APON (ATM PON) is the first PON system that achieved significant commercial deployment with an electrical layer built on asynchronous transfer mode (ATM). BPON. BPON broadband PON is the enhanced subsequence of APON with the transmission speed up to 622 megabits per second. At the same time, it added the dynamic bandwidth distribution, protection, and other functions. APON BPON systems typically have downstream capacity of 155 megabits per second or 622 megabits per second, with the latter now the most common. Types of PON. GPON 10 GPON. As one of the most competitive, the best last-mile solution, GPON Gigabit PON is based on the 2TG.984x standard for the new generations of broadband passive optical access. Compared with the other PON standards, GPON provides the unprecedented high bandwidth downlink rate of up to 2.5 gigabits per second. The asymmetric features better adapt to the broadband data services market. It provides the QoS full business protection, at the same time carries ATM cells and/or gem frame, the good service level, the ability to support QoS assurance and service access. Carrying gem frame TDM traffic can be mapped to the gem frame 8 kHz using a standard frame able to support TDM services. As a carrier-grade technology standards, GPON also provides access network-level protection mechanism and full OAM functions. GPON is widely deployed in FTTH networks. EPON 10G EPON. Like the superheroes of the Hollywood movies, EPON Ethernet PON is the rival activity to GPON, which uses Ethernet packets instead of ATM cells. EPON GEPON uses 1 gigabit per second upstream and downstream rates. It is a fast Ethernet over PON switcher point-to-multipoint to the premises FTTP or FTTH architecture, in which single optical fiber is used to serve multiple premises or users. EPON is an emerging broadband access technology, through a single fiber optic access system, to access the data, voice and video service, and it has a good economy. WDM PON. WDM PON uses multiple optical wavelengths to increase the upstream and/or downstream bandwidth available to end users. WDM PON uses wavelength division multiplexing technology to access to the passive optical network. It has 4 programs as following. 1. Each ONU is assigned with a pair of wavelength for uplink and downlink transmission, thereby providing the ULT to each ONU fixed virtual point-to-point bidirectional connections. 2. ONU uses tunable lasers according to the needs of the ONU to dynamically allocate the wavelength, and each ONU can be shared the wavelength. The network are reconfigurable. 3. Using colorless ONUs, the ONU are independent from the wavelength. 4. Using a combination of TDM and WDM technology, composite pont CPON. CPON uses WDM technology in the downstream, and TDMA technology in the upstream.